Hello, this is Jordan White. This is my presentation for Binary Code Error Correction Project, Week 6. So here's the backstory behind this code. Forgive me for the completely contrived historical scenario. I'm reading the Iliad right now, so you can blame Homer. Godly Telemachus, the son of Odysseus, is angry at his father Odysseus for leaving for the war in Troy, because he left his mother Penelope at the hands of the degenerate suitors. So he decides to betray the Greeks. He knows the constitution of their army and the plan of their attack, but he cannot leave home to warn the Trojans. However, he has carrier hawks, but he can't write a message because he's not yet literate. Fortunately, on a prior visit, he discussed with King Priam the binary codes with error correction theory, because King Priam is an information theorist. Homer just forgot to record that. So he will use his hawks and send them to Troy in single file order. Some will have nothing in their talons, which means that they are zeros, and some will carry laurel leaves, which means that they are ones in binary code. Per Priam's code, the first 2 bits will indicate the cardinal direction of the attack. The next 2 will indicate the presence of archers in the Greek army and whether the army exceeds 3,000 men. Because if it does, then Troy would have to call their allies or something. So here are the first 2 bits indicated here. You can see north, east, south, and west are indicated by the first 2 bits, which gives 4 possibilities of messages. And then the 3rd bit is 0 for no archers, 1 for yes archers. And the 4th bit is 0 if it's less than 3,000 soldiers, and 1 if it's equal or greater to 3,000 soldiers. Okay, so here are all combinations possible, and you can see that there are 16 possible messages given this code. For example, 1101 over here indicates that the army will attack from the south and that there are no archers, but that the number of soldiers does exceed 3,000. Okay, and also I just want to point your attention to the code for the cardinal directions, the first 2 bits. They're cleverly chosen because a single bit error can only communicate a 90-degree inaccuracy. That's because north and south are opposites in all of the bits, and so are east and west. So, for example, if we had a 1-bit error in a communication of east, then either it would communicate north or it would communicate south after that. But 1 bit could not change it to west. This is practical because it would be easier to shift defenses by 90 degrees rather than 180 degrees. So as you can see, this message is efficient because it's impossible to condense this matrix of messages into fewer bits. There are 4 bits, which means there are 2 to the 4th power possible messages, which is 16. And that's exactly how many messages we need. Okay, now Telemachus could send more information if he had more hawks, for example, whether the Greek army has large wooden horses, but he doesn't have more hawks, and also Priam never discussed any other possible messages, so they would not be understood anyway. Now there's a problem. Telemachus knows that with hawks, sometimes one hawk in a sequence will overtake another hawk in flight, meaning those 2 bits become switched. Or a hawk might drop its object, meaning a 1 becomes a 0, or a hawk might steal a new laurel leaf from somewhere, meaning a 0 becomes a 1. Fortunately, Priam knows about these possible errors, and he taught Telemachus how to mitigate such errors by adding more hawks to the end of each message. So this brings in the concept of distance. Priam explained that 2 messages have a certain distance between each other based on how many bits in each position are different. So if we go back to the examples, look at the one in the bottom right, which means they are attacking from the west, and they have archers, and they're over 3,000. This is 1011, and it is a distance of 1 bit from 1111. It's a distance of 2 bits from 1110, it's a problem that the distance is not very great between some of the messages. The reason it's a problem is because if two messages are only one distance away from each other, then an error of 1, for example, one hawk picking up a new laurel leaf, will completely change the message. How do we fix this? Basically, Priam told him that in the case of 4 hawks, or 4 bits, you can add 3 more hawks to the end to make a total of 7 hawks. So let's call the first 4 original hawks H1, H2, H3, and H4. Call the last 3 E1, E2, and E3 for error hawks. And then you can calculate the bit of the last 3 hawks according to these formulas here, and then translate that bit to laurel leaves. What this is going to do is give a minimum distance between each valid code word of 3 instead of 1. This is advantageous because suddenly a 1-bit error will lead to an invalid code word, which is very similar to the original. Thus, you could correct it by shifting to the closest valid code word. A 2-bit error would shift also to an invalid code word, which means you could detect the error because it's still not any valid code. So here's a proof that this setup gives a minimum distance of 3 between each valid code word. Okay, assume you have 2 different codes, M1 and M2. Then there are 3 options. The first 4 bits of both codes either differ by 1, or differ by 2, or by 3 or more, because they're different codes, so they have to differ. Now these are 2 valid codes, that's our assumption. If they differ by 3 or more, then our conclusion is proven that the minimum distance between valid codes is 3. That means 2 cases remain to analyze. Either the first 4 bits of the valid codes differ by 1, or they differ by 2. Let's analyze the first case. The first 4 bits differ by 1. If this is the case, then 2 of the error bits will differ as well. Here's how we know that. There are 2 cases. The bit that differs is either H1, H2, or H3, or the bit that differs is H4. In the first case, let's see what happens. If the bit that differs is H1, then we see that the error bit E1 and E3 will both flip. E2 will stay the same. Thus, 2 of the error bits will flip, meaning the new minimum distance is 3 because H1 differs, E1 differs, and E3 differs. We can see by symmetry that this will happen if H2 differs or if H3 differs. But what if H4 differs? In that case, all 3 E bits will differ because H4 is present in all of the error bits. That will make a total difference of 4. Thus, the first case is proven that when the first 4 bits differ by 1, the total code word differs by 3 or more. In the second case, assume that the first 4 H bits differ by 2. Then there are 2 more cases. Either one of the differing bits is H4, or both of the differing bits are H1 to H3. In that first case, if one of the differing bits is H4, then we can see that, say, the other differing bit is H1. That means E1 and E3 will stay the same, but E2 will flip. In that case, we have 3 differing bits, 2 H bits and 1 E bit. By symmetry, that works if the other differing bit is H2 or H3. In the second case of the second case, if none of the differing bits is H4, then say that the 2 differing bits are H1 and H2. That means E1 will stay the same, but E2 and E3 will flip. By symmetry, that works for any combination of 2 among H1, H2, and H3. Thus, in this case, the total number of differing bits will be 4. Okay, so that is an exhaustive proof that in each possibility, 2 valid code words differ by at least 3 total bits. Here's why a minimum distance of 4 is not much better. Because any code word in a system of minimum distance 4 will have one error that can be corrected by this formula. 4 minus 1 is 3, over 2 is 1.5, and the floor of that is 1. This is the same number of errors that can be corrected for minimum distance of 3. So the additional space of requiring minimum distance of 4 doesn't improve the error correction. Of course, you could then detect messages with 3 or fewer errors instead of only 2 or fewer errors, but this might not be worth the additional space requirements. Okay, let's look at the topology now. The topology will be on the space V7, which V is the space of 2 bits, 0 and 1, and then take that to the power of 7 to get all possible 7-bit combinations. The topology generated by this distance metric is the topology on V7 that has, as a basis, all open balls, and inside of that ball are all of the codes within a distance of that radius from that center code. So we know that this generates the discrete topology because each code exists in an open ball that is the singleton set with radius of 0. We also know that the subset of valid code words inside of V7 is totally separated. It's very separated because they're all a distance of 3 from each other. All right, this topological interpretation has many practical applications. Let's say we receive a message that we think might have an error, and we know for some reason that at most 4 errors could have occurred. Then we could take the ball around that message with radius 4 and apply the subspace topology, and this will restrict our focus to only the possible original messages that could have been sent. Or perhaps we have a prior probability distribution, which describes how likely it is that each possible number of errors could occur. Then this would help us optimize the topology for very large code spaces with many different symbols or dimensions by restricting our open sets to describe only those error messages that are likely to have occurred from a given original message. So in conclusion, the war ends with a Trojan victory, and the result is tragic for the history of Western civilization. And now you know why I do not write epics. Thanks.